Okay, so my name's Colin Eberhardt. I work at a company called Scott Logic, and yeah, we're hiring. I said so at the table at the back. And a little bit about me, I'm another CTO with a physics degree, so, you know, take from that what you will. So, WebAssembly, hands up if you've heard of or know what WebAssembly is. Okay, reasonable show of hands. So I first did a WebAssembly talk around about a year ago, and most people hadn't really heard of the technology. Now, I think a lot of people have heard of the technology, but from having a bit of a conversation with a few of you around the room, people have heard of it, they're a little bit unsure as to what it actually is. And I've taken this quote directly from the WebAssembly website, and I think in this single sentence it sums it up pretty well. So, calling out a few key things. It's a size and load time efficient format. So, if you think about the way that we currently deploy code to the web through JavaScript, it's a little bit inefficient. We send it to the browser in a text-based format, and the browser then has to parse that, convert it into an abstract syntax tree, runs it in an interpreter, then through various levels of JIT optimization, and eventually we get something which runs really, really fast. But the problem is, it's kind of eventually. It takes a long time to get up to speed. WebAssembly was designed with the way that we deploy applications to the web in mind from day one. So that's where the size and load time efficient format come from. Suitable for compilation. Now again, JavaScript, the JavaScript you write is almost certainly compiled in some way when you deliver it to the web. It doesn't matter whether you're using Babel to go from one flavor of JavaScript to another, or TypeScript, or potentially using a different language compiling to JavaScript. We pretty much, all of us here, are compiling JavaScript at the moment. And the final bit at the end, to the web, that's just wrong, actually. WebAssembly was designed as a web runtime. It's actually used in a number of other places as well. It's being used as a smart contract engine on blockchain. People are using it as effectively an operating system in its own right. So that's WebAssembly. It's an open and cooperative specification, and it's out there at the moment. You can run it in your browser, in Node, and all over the place. So that's a little bit about WebAssembly. So why create a WebAssembly compiler? A few different reasons. First is Stack Overflow published the results of the developer survey a few weeks ago, and there was a really interesting result. Under the most loved languages, WebAssembly was 5th on the list. And the thing that's a little odd here is all of the other languages on the list are ones that you or I might actually write in our day-to-day job. WebAssembly isn't something that most people will actually write. It's a compilation target. So it was a little odd to see a compilation target listed as a loved language. And to me that made me think, well, as it's going to have a big impact on what you do in the future, it's probably a good idea that you learn a little bit more about what WebAssembly actually is. And that's why I, for my own benefit, had a go at writing a compiler to see what WebAssembly is under the hood. Also, part of this talk is for you guys to teach you something. Yeah, it's true, I have. But part of it was for my own learning, for my own benefit. I don't know if other people have a kind of programming bucket list. There have been certain things that, as a developer, I've always wanted to do. Meet Brendan Ike. Write an emulator. And recently I actually wrote a Chip 8 emulator that targets WebAssembly. And the nice thing about WebAssembly is it's quite small, it's quite simple. So you can achieve some quite interesting things when you target WebAssembly. So on my bucket list, I've always wanted to understand how compilers work. And as I mentioned, I'm from a physics background. I kind of drifted into software by mistake. I didn't actually get taught the basics and the fundamentals. So for me, it was an excuse to have a dabble, find out what parsers are and all that sort of thing. So I submitted a talk to Full Stack New York about 6 months ago. I said, yeah, I'm going to write my own WebAssembly compiler and teach everyone about it in a 20-minute talk, fired it off and forgot about it. And then about 2 months ago, they came back and said, yeah, that'd be great, actually. Right. So I've spent a lot of time in my evenings coming up with this. My goal was to create a programming language that wasn't fully feature-rich. What I wanted to do was render this thing, the Mandelbrot set, a fractal. So I only added the language features that were required to reach this one goal. And that was the language I developed, and this is the talk about the language. Now, one thing I'm going to do is apologize in advance. I'm experimenting on you guys because the talk I've got at Full Stack in 3 weeks' time is only about 25 minutes. And I'm going to tell you everything about how to create a compiler for this language. So If it takes 2 or 3 hours, I apologise. And if you've got any feedback and any hints, if there are some massive sections that you think, just drop that, let me know. If you start falling asleep, I won't be offended. So let's start from the very beginning. Let's create the simplest and smallest WebAssembly or WASM module we can. So, WASM modules are a binary format, so this is quite different from JavaScript, which is a text-based format. So it's delivered to your browser as a binary. Typically, it's delivered as a WASM file. However, you can construct the binary format in memory, and that's what I'm doing here. This is the simplest WebAssembly module that's fully formed and valid. It consists of a module header, and if you know your ASCII, that actually spells out ASM for some reason, and it also has a version number so that they can maintain backwards compatibility in future. So that's the simplest WASM module. How you use it is as follows. So we've taken our WASM module and then we instantiate it through the WebAssembly API. So we instantiate it through its hosting environment, which is JavaScript. So the interesting thing here is that WebAssembly has a close and symbiotic relationship with JavaScript. It runs alongside the JavaScript virtual machine in its own virtual machine. And as you'll find out shortly, they share various things through a number of different interfaces. So the above example is a trivial module which returns an executable that does absolutely nothing. So let's try to do something a little bit more ambitious. This time we'll create a WebAssembly module that provides an add function that just adds a couple of numbers together. So let's have a look at what that might look like. So WebAssembly is a binary format, but unless you really like looking at hex codes, it's much easier to understand WebAssembly through the WebAssembly text format. And there's almost a direct one-to-one mapping between the text format and the binary format. So they're very, very similar. So this is a valid WebAssembly module that exports an add function that adds two float values together. So what you can see from this is that WebAssembly has a relatively simple instruction set. There are around about 60 instructions. If you've done any assembly language programming, it's got that kind of feel to it. It only has 4 numeric types. It has 2 floats and 2 integer types. It operates via a stack machine. So if you notice the way that add is working, the first thing it's doing is getting the local at index 0, then the local at index 1. That's the 2 parameters passed into the function. The add operation pops 2 values off the stack, adds them together, and pushes a value onto the stack again. So everything is stack-based within WebAssembly. And finally, probably the most important point to learn here is WebAssembly has no built-in I/O at all. So WebAssembly on its own cannot access the DOM, it cannot access the file system, it can't do anything on its own. It needs to work with its host environment to do something useful. So how do we encode that simple add function in JavaScript? So here is my code, which is an array of bytes. The first one here is get local 0. So I've got an enumeration of my different opcodes, and what I'm doing here is unsigned leb128 is an encoding, it's a variable length encoding for integers. So what I'm doing here is encoding in binary get local 0, get local 1, and the add function. Add operation, shall I say. Then I'm encoding it as a function. So the way the binary format of WebAssembly has various encodings, and to be honest, they're all really quite simple. If you have if you have various arrays of bytes, it encodes the length at the beginning, and then the bytes follow afterwards. WebAssembly itself is made up of a number of different sections. The most important one is the code section, which we're populating here. This is your executable code. It also has export sections, import sections, and various sections that define the various types that are being, well, type signatures that are being used. It's relatively long-winded to create this sort of thing in JavaScript, but the concepts are really quite simple. So if we put this all together and instantiate this module, it now exports an add function which we can invoke from the JavaScript host. And finally, if we were to write that to a WASM file, which is the typical way to deliver it, this is what the binary would look like. So that is how to create a really quite simple WebAssembly module through code. And that's our first step towards creating a JavaScript compiler that takes a language and compiles it to WebAssembly to execute within the browser. So the next step, building a compiler. Before launching into the internals of the compiler, I just want to get some of the terminology out of the way. So this is the language that I created. It's not a terribly creative language, it's fairly familiar looking. It's made up of a collection of statements. So here you see a variable declaration statement. This statement basically declares variable b is assigned to the initial value of 0. We have variable assignment statements where we assign the output of an expression to an existing variable. We also have while statements. So the interesting thing here is statements can have other statements nested within them. And on the right-hand side, we see expressions. So the fundamental difference between the two is expressions return values, whereas statements are void. They do not return a value. That's the key difference between the two of them. And also here we can see that expressions can be constructed into tree-like objects, which evaluate to a single result. So that's some of the language out of the way. Now, if you've ever come close to a compiler, you'll have probably seen that there are some fairly standard building blocks. There's a fairly standard pattern for putting a compiler together. First is the tokenizer. So the input is your code in string form. First you have the tokenizer, which splits it up into tokens, which we'll see shortly. You have the parser, which creates an abstract syntax tree. Then you have the emitter, which emits, in this case, our WebAssembly bytecode. So we'll start with the tokenizer. Now, the tokenizer itself is relatively simple. It's only about 30 lines of code, but rather than show you the code, I thought it's probably easier to show you what the code does dynamically. So, my tokenizer matches a number of patterns which are encoded as regular expressions. So the top one here matches numbers. The next one matches just a couple of keywords at the moment, and this grows over time as I increase the vocabulary of my language. And the final one matches white space. The bottom is the input. This is my language. And the right-hand side is the output that the tokenizer builds up. So the way the tokenizer works is it passes through the code of my application using a cursor. So it starts at the beginning and matches the patterns. The first pattern to match is white space, which does nothing. The next pattern that matches is my keyword pattern. So this pushes a token to my output, a keyword token. Next up, we find some more white space. Following that, we match a number, which is added to my tokenizer output. And finally, we reach the end of the string. So this is the output of my very, very simple tokenizer, a list of tokens. So what this has achieved is it's taken away some of the superfluous information in my code, the white space, which has no semantics, it has no meaning in my language, so that's been disposed of. Other than that, it's a relatively simple task. So here's the final output. Next up is the parser. So I'm taking the output of my tokenizer and parsing it. So there's going to be a little bit more code here, but I've tried to keep it a little bit lightweight. So the parser does a similar thing to the tokenizer. It iterates through its input as an array. So it iterates through the tokens that have been supplied. So this is the input on the right-hand side. So it maintains a pointer to the current token, which you can see on the slide. It also has a utility function called eatToken. What this does is it takes the current token and disposes of it. I have no idea why parsers eat tokens. Every parser that I've looked at has an eatToken function, and no one's ever told me why they eat them. It's such a weird thing to say, but that's what they do. There's some code that I'll elaborate on shortly. And finally, the main body of my parser is the iterator, which iterates over the statements. So basically, my parser is saying, I expect a collection of statements to be present in my tokens. So the first thing it's doing is it's parsing a statement. So it's matching on the token type, which is a keyword. It's matching on the value of my keyword, which in this case is print. It's eating a token, which is advancing it to the next token, and its return value is a node, which will be the starting point of my abstract syntax tree. And my print statement takes an expression. That tells the runtime what it needs to print. So the next thing the parser does is it parses the expression. So we'll look at the expression parser. Again, it's really, really simple. Here it switches on the token type, and in this case it's just a number. It converts the string into a numeric type and returns that as a node, eating a token. this is a really, really simple token input and a really simple abstract syntax tree output. But what you can see here is the abstract syntax tree is a more structural representation. It has a lot more meaning to it. The abstract syntax tree is something you could potentially pass off to an interpreter that could actually interpret and execute your application. In future, we'll see the abstract syntax tree grow into something a little bit more complicated. So finally, the emitter. So we've gone from tokens to abstract syntax tree. The final thing is the emitter that takes the abstract syntax tree and converts it into a WebAssembly module. Now you've already seen an emitter. That's what I showed you at the beginning, but not one that's driven from an abstract syntax tree. So here is an updated version where I'm taking my abstract syntax. I should pick easier terminology, abstract syntax tree. So we're taking the tree and we're converting it into a WebAssembly module. So again, we're iterating over the statements in the input, and we're matching on the first one, which is a print statement. And before we actually convert the print logic into WebAssembly, because WebAssembly is stack-based, we need to compute the result before we invoke the print statement. So what we're doing here is we're emitting the expression before we're emitting the code, which is the WebAssembly encoding of the print statement. So we've moved on to the expression emitter, and here, at the moment, all we have is number literals, and we're outputting, hopefully, some WebAssembly that's vaguely familiar to you from the previous slides. We're outputting an opcode, which is a constant of the value given in our abstract syntax tree. So, demo time. So this is the state of the code at that point in time. I've got all this code on GitHub, and I've actually got a commit at each point that I'm doing a demo. So if you want to do your homework, and revise this stuff, you can actually check it out at various locations and see the whole thing up and running. So if I'm lucky, what's your favourite number? Pick a number.
78.
78. If we're lucky, we run the compiler. Yay, yeah, I'll put 78. Do I get a small round of applause for that? No, not too big, not too big, not too big. It gets better. Hey, I was at the Panto just a few days ago, so I'm all for audience participation. So don't peak too soon. So that's our really, really simple language. All it has is print statements that output numbers. And just to demonstrate, we can actually print multiple outputs, but we can't do anything terribly useful. So to be honest, I put in quite a lot of effort to create a parser, a tokenizer and parser and an emitter to do something really quite trivial. But the useful thing here is that by putting those building blocks in place, we can actually build on that really quite rapidly. So what I'm going to do is fairly rapidly layer on a number of other concepts, and you'll see hopefully that the building blocks I've put in place should support that. So again, just to hopefully round this off, this is what's happening on that simple program. On your left-hand side, this is the array of tokens as outputted by the tokenizer. The parser converts that into the abstract syntax tree. The emitter outputs the wasm that you see on the right-hand side. So let's try to do something a little bit more interesting. Let's do some simple maths. And in order to do that, we need a slightly more rich expression language. At the moment, our expressions are just number or numeric literals. So I'm not going to go back to the parser. You've seen already the parser is just a bunch of regular expressions. I'm sure you can come up with a regular expression that matches a bracket as long as you remember the right escape sequences. So the tokenizer can now recognize parentheses and operators. Now, jumping back to the parser. The parser can parse statements and expressions, so we need to build on the expression parser to be able to understand brackets effectively. So let's have a look at this section. The first thing it does when it encounters a bracket is it eats the token. Now this is an interesting thing. The brackets are present in our tokens, but they're not present in the abstract syntax tree. The brackets don't actually convey any meaning, and we remove them in this process. And also, our expression parser is recursive. So the way what it does when it encounters a bracket is it eats the token, it parses the next expression that it finds, it stores the operator, it eats another token, which is the operator, and it parses the right-hand expression. It's only a few lines of code, but this allows us to build up deeply nested expressions. So jumping to the output of print 42 plus 10 divided by 2, this is what the abstract syntax tree looks like in that case, just by adding about 5 lines of code to the parser, which is quite cool. So what does that mean for the emitter? So now we need to take that abstract syntax tree and convert it into a WebAssembly module. So a few key differences here. The first one is I've introduced a traversal algorithm. So hopefully most of you will be familiar with the concept of the visitor pattern or tree visitors. So given a tree, a visitor will visit each of the nodes and will invoke a function on each of the nodes. In this case, we're using a post-order traversal, which visits left, then right, then root. And the reason it does that, again, is because WebAssembly is a stack machine. Root encodes the operation, and left and right are the operands. So by using a post-order traversal, it will output the WebAssembly code in the correct order for the stack machine. So we've got our number literals already, you've seen that previously, and for the binary expression, all we need to do is push the correct opcode. So again, that's just a simple little lookup. So I'd say maybe another 10 lines of code in the parser, another 10 lines of code in the emitter, and I can now actually evaluate expressions. So let's have a look at that with the demo. I'm one-handed typing because I'm holding a mic, so bear with me. So let's just divide that by something or other and run the compiler. And I'm sure you all knew 78 divided by 3 is 26. This is pretty cool. Round of applause? Just a little one. So the time I invested in putting in place the parser and the tokenizer and the emitter is now starting to reap some rewards. By adding a few lines of code, I can do something actually quite useful. So variables and while loops. I'm going to accelerate a little bit here and add a few more concepts, but without diving into too many of the details. So variables. These map quite closely to some pre-existing WebAssembly concepts. So WebAssembly, the code within your WebAssembly module is arranged into functions. Functions have a number of input parameters and a single return value. They also have locals, which are scoped to the function. So what you see here is a function where we have declared that it has a single local value, which is of type F32, a 32-bit floating point. And I know this is a fairly silly piece of code where you declare a variable to have the value 23 and then you print it immediately. If you had an optimized compiler, it would get rid of all of that lot. My compiler is not optimized. And this is the WebAssembly equivalent. So we've pushed the constant 23 onto the stack. We've used the setLocal opcode to set the local at the 0th index of the function to that value. We're then immediately getting it again, and we're calling the print function. So WebAssembly has locals. They're not named as they are in many languages. They're index-based, but it has local variables. So changing the emitter to support this is really quite simple. In my compiler, or the emitter part of my compiler, I just have a symbols table where I basically say F is at index 0, G is at index 1, and I replace them as I encounter them in the AST. While loops. Again, WebAssembly has looping logic. Now it doesn't have while loops, it doesn't have for loops, but it has a loop of sorts which you can bend to recreate these concepts. And this is what happens quite often when you create a compiler. You have concepts which are similar but not quite what you want, and you have to bend them a little. So if we look on the left-hand side, this is the looping syntax in my language, while and end while. Very creative, I know. On the right-hand side, this is the WebAssembly equivalent. So WebAssembly has the concept of blocks, and you can have multiple nested blocks within functions. And it has the concepts of loops. The way that it actually works, which is a little bit odd, is it has a branching construct. And the branching construct branches to a stack depth. So the br_if branches if the value of the stack is, I think, falsy or true. So it branches based on the current value at the top of the stack to a depth of 1 in this case. So that will branch out of the loop back into the block. The following one is a non-conditional branch to a stack depth of 0, which means at the same depth. This is how you create looping constructs, and you can use this to create while loops and for loops. I'm not going to show you the actual emitter output for this. It's a bit boring. It's about 20 lines of outputting binary, but this is effectively what it's doing. Let's have a quick go at that. So we should now, I'm going to curse this one-hand typing. I should be able to declare a variable, f equals 0. I should be able to now create a while loop. While. Now, one thing to note is you'll notice that my language is quite bracket heavy, if you will. I only support binary expressions, and I haven't bothered implementing bidmas or bimdas or bodmas or whatever it was when you were taught it at school. Interestingly, the bidmas logic is something you should be able to implement in the parser and not actually have to update the emitter, which is quite interesting, if you find that interesting. Pull requests are welcome. One-hand typing, there we go. So we're going to be incrementing f, and if I print f, cross my fingers, there you go, that's the output. So again, each time I'm running that, thank you. Whew. So finally, with the constructs I've created so far, I've got variable declaration, I have variable assignments, I've got while loops, I've got expressions. That's actually all I need to create a Mandelbrot fractal. You don't need much in the way of language constructs to render a fractal. The one missing piece is writing to the screen, and for that I created a setpixel statement within my language. Now, this is where it gets a bit tricky. As I mentioned, WebAssembly doesn't have any native I/O, so at the moment, with what you've seen so far, you can't actually create that. So this gives you a bit more of a well-rounded view of the WebAssembly virtual machine, which is on the left-hand side, and the JavaScript virtual machine or host is on your right-hand side. So at the moment, you've seen the parts in grey. You've seen the program memory. That's where your WebAssembly module lives. That can push and pop values to the execution stack. So that's where your function calls live. That's where the locals live. So one other part of WebAssembly that is really, really useful is linear memory. So linear memory is a bit like the heap in other programming languages. It's not really a heap, but you can use it like a heap. Interestingly, the stack and linear memory are completely separate. So what that means is you can't cause your stack to overwrite your heap. So it removes that class of security vulnerability. So there are some WebAssembly instructions for reading and writing values to linear memory. I've included a couple of examples that just read and write 32-bit integers. There's a whole family of them, basically writing values of different bit depths. The interesting thing about linear memory is it's shared with the JavaScript host. And quite literally, you can read both WebAssembly and JavaScript can read and write directly to linear memory. It's accessible through in JavaScript as an array buffer. So what that means for my application is, I don't know if you've ever used some old computers, things like the BBC Micro. They used to have the concept of video RAM. Basically, there was a location in RAM that was sent to the raster scanned and sent to the screen. We can set up exactly the same thing here. I can decide that this location in memory is my display in my screen. Also, if you're writing a more powerful language with a WebAssembly compiler, you probably want things like strings or structs or objects. Now, if you're writing a Rust application that targets WebAssembly, that will use linear memory as a way of transferring larger blocks of data between the JavaScript host and WebAssembly. So let's try that final demo. I'm not going to type it out. I'm going to hit refresh, and yeah, I'd have been here all night. So that is the Mandelbrot set. You'll all recognize that. Was it z squared plus c or whatever it is? Yeah, imaginary numbers. And if I hit the button, that compiles it. Yeah! As you can imagine, the first time that happened, I was like, yeah! And my wife was like, what are you doing? It's WebAssembly, you know, it's awesome. Yeah, so we finally got there. So as a quick recap, and a few maybe more important points. WebAssembly is a relatively simple virtual machine, and that's one of the things I quite like about it. I've been writing software for years and years and years. I started on the BBC Micro, and what I quite liked about the BBC Micro is I could get the schematic for it, and I understood it. When I wrote applications for it, I knew where they went, down to like which wires they went down, which is pretty cool. More recently, I've been doing a lot of web development, which is awesome and great, but there's so much I don't understand, and there's so much I don't think I'm ever going to understand. I'd love to know how React works under the hood. Probably haven't got time to do that. Whereas WebAssembly, the simplicity of it means it's actually really quite easy to understand all of it. It's also, as I said, it's a fun playground. If you've ever wanted to write an emulator or something like that, it's a great place to get started. As an aside, TypeScript is great. I use TypeScript throughout in this project, and what I really enjoyed with TypeScript is the structure of my abstract syntax tree. I could encode that entirely as types within TypeScript. I could be quite rigorous about the type checking and get rid of a whole load of errors. Also, creating a simple compiler isn't that hard. I'm not going to say creating compilers isn't hard. I'd be foolish to say that. Another thing, I personally found it a good way to exercise my programming skills. You'll find a lot of common patterns appear in compiler design. Things like the visitor pattern, tree traversal. I also found it a good way to just practice things like simple stuff like unit testing. Also, finally, there's a lot of creative energy being poured into WebAssembly at the moment. It's a very new topic. It was only the working group behind WebAssembly came together in 2015. The first version was launched last year. If you're looking for an opportunity to break new ground and do something interesting, WebAssembly is a good place to start. So finally, on my bucket list, I can tick off create my own language. So I need to add something new to my bucket list. So that's create a self-hosting compiler. And the reason for that, you might not know what that is, and I had to look it up. When I started on this talk, I shared my joy on Twitter and said, hey, I'm going to create my own language, and here's a quick example. The first reply I got was, is it self-hosting? And self-hosting is a compiler that can compile itself. And it sounds crazy. There's actually a lot of good reasons to create a self-hosting compiler. No, my compiler is not self-hosting. I don't even have strings. And to be honest, that's on my list. One of the things I'd like to move on to is strings, because that gets you into another interesting topic. Do I garbage collect, or do I just have, do I create a memory allocator? For me, you know, this is the first step on a bit more of a journey. And to kind of demonstrate that, over the past couple of days, I've been fiddling around, and I don't know, did anyone here ever do create demos on things like the Amiga and stuff like that? I used to be a demo coder, and this was one of the first demos I created. Nice flashy patterns. Yeah, keeps me occupied when there's reality TV on. And that's it. Yeah, if you've got any questions, I mean, hopefully that's inspired you to at least have a play with WebAssembly. And if you've got any questions about this, or maybe even some more practical things about WebAssembly, let me know. Thank you very much.